Good day to all of you. So we're already on chapter 19 of the Operating Systems lecture series, which is all about network and distributed systems. So for discussion, we will be discussing all about the network systems and of course the more sophisticated, which is called the distributed system. So let's start our lesson. So again, chapter 19 is all about network and distributed systems. So the contents of chapter 19 are advantages of distributed systems, network structure, communication structure, network and distributed operating systems, design issues of distributed systems, and distributed file systems. So the objectives of this chapter are explain the advantages of network and distributed systems, provide a high-level overview of the networks that interconnect distributed systems, define the roles and types of distributed systems in use today, discuss issues concerning the design of distributed file systems. So for the overview for this chapter, so definition of a distributed system is a collection of loosely coupled nodes interconnected by a communications network. So these nodes, variously called as the processors, may it be computers, machines, and hosts. And then site is a location of the machine. Node refers to specific system. So generally, a server has a resource, a client node at a different site that wants to use that mentioned resources. So this is an illustration of a sample distributed system. So as you can see here, in site A, we have the server, and then we have site C, we have the resources, and then in site B, we have client. So by means of distributed systems, this can connect by means of the network. If they can, for example, the client can request services from the server and can also use the resources even though they are at different sites or locations. So that is the characteristics of a distributed system. So the components of, for example, the server, the client, and resources does not need to be at the same location as long as they are connected to a network. So nodes may exist in a client server, peer-to-peer, or hybrid or combination of both configuration. So in client server configuration, server has a resource that a client would like to use. So that's the model for client server. And then for peer-to-peer configuration, each node shares equal responsibilities and can act as both clients and servers. So example of a peer-to-peer or P2P, if you're familiar with downloading torrents. So if you have, for example, you have a copy, a 100% copy, you can be as a server, and then while you're downloading, you are a client. So that's why peer-to-peer, meaning the term peer-to-peer, it's like friends, meaning they have equal responsibilities compared with client server. You can you can relate client server for a mother, and then client for example a child or a baby. And then communication over a network occurs through message passing. So how this message passing is done? You can visualize it. For example, you're in a jeepney and you're going to pay your fare. So if you're going to pay the fare to the jeepney driver, and you're on uh, the last seat. Okay? So, how are you going to pay for the driver? Are you going to walk into the driver and pay the fare, or you're going to call the attention of your co-passenger and let him or her pass your fare? So the notion here is you're going to pass the fare one into another until it reaches the jeepney driver. And then, for example, if you have a change for your fare, will the driver go out of his way while driving and give you your change? No, it will also pass the change of your fare to the co-passenger adjacent to the driver, and then it will pass until it reaches to you. For message passing, of course, if you're not the intended recipient, you're going to pass it to the next node for this example. So the analogy here is just like what I'm saying with you're paying fare for your ride in a jeepney. And then all higher level functions of a standalone system can be expanded to encompass a distributed system. So reasons for distributed systems. So first is we have resource sharing. So sharing files or printer at remote sites. So that's the one reason for resource sharing. So of course, it is very convenient if you're going to share files not to have a separate copy for each computer. What if this computer modified his or her copy? How can that be updated to all the other copies that is exist, for example, at a remote site or printing? You have one printer. If sharing is not possible, are you going to buy a separate printer for each of the computers? So it's very expensive. So it's better to share through a network the printer so that it will be, of course, less cost for example, for the company. And then processing information in the distributed database. That's also the reason for resource sharing. And then using remote specialized hardware devices such as graphics processing units or GPUs, because not all computers have this specialized hardware. So if you're going to resource sharing, so it will have an impact. It will be more efficient and less cost. And then another reason for distributed system is computation speed up. Distribute subcomputations among various sites to run concurrently. Of course, two heads are better than one. So for a distributed system, if it has two or more um, computers, so the computing power will be much greater than a standalone computer. And then we also have load balancing, so moving jobs to more lightly loaded sites because the nodes, which of course can be processors, computers, machines, or hosts, since they're acting as one, so for load balancing, if this particular server has many tasks that has to be done at once, what the distributed system will do is that it will distribute the other jobs of that server so that there will be load balancing. And the next is we have reliability, detect and recover from site failure, function faster, and reintegrate failed site. So reliability. So distributed systems, of course, an example is the internet or the World Wide Web. So if there are an instance, actually I've experienced it when Yahoo Philippines is still existing. Okay. So there are times, for example, you are accessing yahoo.ph, and then I don't know if if you can notice that there is a time in which if you go to Yahoo Philippines, it will be redirected to Yahoo US or Yahoo Singapore. So what's the meaning of that? There is a possibility that the server for Yahoo Philippines is down. So as a distributed system, instead of displaying of course, the server cannot be reached or any other um, error for because the server is down. So it redirects to other sites. So of course, so it's also an impression. Wow, the Yahoo Philippines or the Yahoo site is never down. Of course, there is a as a machine, there will always be um, server downtime, but it's up to the distributed system. How does this efficiency will work? For example, for clients, for us, that we will not have a bad impression of the site. Okay, next is we have the network structure. We have the local area network or the LAN designed to cover small geographical areas. Example, in a computer shop, so that's already a LAN. The internet in a campus or the network at a campus, it's also a LAN. So consists of multiple computers, may it be workstations, laptops, mobile devices, peripherals, printers, storage arrays, of course, this can be shared, and routers providing access to other networks. So, as long as the device can connect to the network, so may it be, of course, workstation, laptops, mobile devices. And then Ethernet and or wireless or the Wi-Fi or wireless fidelity, but it's not true anymore to its name because Wi-Fi, if there's an obstruction, then the signal will be lessened. It is the most common way, those two Ethernet, the cable connection, and of course the wireless connection, the wired and the wireless connection. These are the most common way to construct LANs. So Ethernet is defined by standard IEEE 802.3 with speeds typically varying from 10 Mbps to over 10 gigabits per second. Of course, it's faster than Wi-Fi because it's a wired connection. So the connection using wired optical cables are of course more reliable than wireless connections. On the other hand, Wi-Fi defined by standard IEEE 802.11 with speeds typically varying from 11 megabits per second to over 400 megabits per second. Of course, both standards constantly evolving because, of course, technology is also evolving. So we have this an illustration of a local area network or LAN. So we have a tablet, for example, then a mobile smartphone, and then laptops, and then it's connected to a wireless access point or WAP, and then this is connected to the router. And from the router, we have the server, and then a computer, and then a printer. And then this router can be connected through the one link which you connected through the internet. But is it possible for a LAN to have no internet connection? Actually, it's really very possible uh, that you have a LAN network even without an internet connection. So next is we have the wide area network or the WAN. So links geographically separated sites. We have the point-to-point connections via links. So examples of this are telephone lines, list or dedicated data lines, optical cable, microwave links, radio waves, and satellite channels. So what is this? Of course, you're familiar with telephone lines. What is this list or dedicated data lines? So these are also just our consumer internet connection that is provided by our internet service provider, but it's more expensive. Why it's more expensive? For example, your bandwidth is 20 mbps, and it's not a list or dedicated data line. So of course, for example, you're paying for example 1,000 example, and then 1,000 pesos, and then for the dedicated, the same mbps, but example it costs 2,000. What is the difference between the two? Okay, the difference between the list or dedicated data line. The problem with the typical internet connection is that if there are more users who are using the internet connection, it will be slower. But for a dedicated data line, even though people are using the internet provided by the ISP, his or her bandwidth will not be affected. So that is the difference of dedicated or list line. Example of that is when of course when our internet connection is relatively not that fast. I think it's for the time is from 4 to 5, 4 to I don't know 4 to 8. At that time 4 to 8 p.m. the internet is very slow because there are also many users who are using the internet connection at that time. But if you can notice, if you're going to wake up 12 in midnight until morning, you really can notice that it's very fast. It's because no few people who are awake at that time are using the internet. So it means that if you have an internet connection provided by your ISP, and it happens to you in that fashion, or you have an experience like that, so it means that your subscription is not a list or dedicated data line. And then of course we have the optical cable. So this is faster than the typical cables that we're using. And of course there are others such as microwave, radio waves, and of course the satellite channels. So these are implemented via routers to direct traffic from one network to another. So so we have this the router. So this one. So this can connect to one. Every network, if you have to have an internet connection or connect to other networks, you should have a router. Then the internet or the World Wide Web, one enables hosts worldwide to communicate. And then speeds may vary. So many backbone providers have speeds at 40 to 100 gigabits per second. And then we also have the local internet service provider or ISP, as I've mentioned, may be slower. And then one link's constantly being upgraded because, of course, of the technology. And then WANs and LANs interconnect, similar to cell phone network. So cell phone use radio waves to cell towers, and towers connect to other towers and hubs. So also an example of wide area network is in our campus at Bat State U. So that is there is already a centralized, though it have in an enrollment system actually. Um, the central server is at the main, and then when the enrollment system is not yet online, and then the enrollment system that is installed, the interface that is installed in the computers here at another campus can access all the files with the information, the database is not locally available at the campus, but it is centralized in the main. So that's also an example of wide area network. So of course, so wide area networks, you can only connect from wide area networks using routers. So that's the R here. And then we have the network host. And for this example, we have the network host here, can be illustrated. We have the host operating system and of course the user processes. Okay, next is we have naming and name resolution. So each computer system in the network has a unique name, of course. So may it be by means of an IP address or a MAC address. So later on, what is a MAC address? And then each process in a given system has a unique name or process ID. And then identify processes on remote systems by. So for this particular process, we should include in the ID the host name and the identifier pair. And then we have the domain name system or DNS, specifies the naming structure of the host as well as name to address resolution. So I've already discussed DNS, but for your to refresh your minds, so DNS is used for us for the ease of memorizing the names of sites. Example, Facebook.com. It has an IP address for the server. What do you want? What is easy to remember? The IP address of the server of the Facebook or the name www.facebook.com. So it's easier to remember if the site, if you're going to type the name of the site, then its IP address. So the one is responsible of translating the IP address to its name of the site is by means of the DNS or the domain name system. Okay, next is we have the communication protocol. So the communication network is partitioned into the following multiple layers. So layer 1 is the physical layer. It handles the mechanical and electrical details of the physical transmission of a bit stream. So mechanical and electrical details, so it's mostly the hardware component. And then layer 2 is the data link layer, handles the frames or fixed length parts of packets, including any error detection and recovery that occurred in the physical layer. And then layer 3 is the network layer, provides connections and routes packets in the communication network, including handling the address of outgoing packets, decoding address of incoming packets, and maintaining routing information for proper response to changing load levels. So continuation with the layers. And then layer 4 is the transport layer. responsible for low-level network access and for message transfer between clients, including partitioning messages into packets, maintaining packet order, controlling flow, and generating physical addresses. And then layer 5 is session layer, implements sessions or process-to-process communications protocols. And then layer 6 is the presentation layer, resolves the differences in formats among the various sites in the network, including character conversions and half duplex or full duplex, or this is used for echoing. And then next is we have the application layer, interacts directly with the users, deals with file transfer, remote login protocols, and electronic mail, as well as schemas for distributed database. So we have the OSI network or network model, or the open systems interconnection model. So logical communication between two computers with the three lowest level layers implemented in hardware. So network link and physical layer are in hardware. So we have computer A and computer B, and then we have an application that is used by the user. For example, if you want to message computer B, so you have an application, for example, a messenger app, and then it will pass, for example, you send a message, it will go to the application layer, then presentation layer, session layer, transport layer, network layer, data link layer, and physical layer. So these three, which is already in the hardware, and then this will be connected to the data network, and it will go to just like with this one, but in a reverse fashion. So for physical, link, network, transport, session, presentation, application, and computer, the user in computer B will receive the message. So that's how the example for this one, message passing, works with two computers that are connected by using the OSI network model. Okay, we have the OSI protocol stack. So for this one, so of course, this is where the user interacts with the system. So end user application process, and then between them is the distributed information services. And then inside the application layer, what can you do is file transfer, access and management, document and message interchange, job transfer, and manipulation. Then between application and presentation layer is we have the syntax independent message interchange service. So what can you do in the presentation layer? We have transfer syntax negotiation and data representation transformations. And then in the session layer, this is where the dialogue and synchronization control for application entities. And then between session layer and transport layers, we have the network independent message interchange service. And then what happens in the transport layer is the end-to-end message transfer, connection management, error control, fragmentation, and flow control. And then next is the network layer, wherein the network routing, addressing, and call setup and cleaning is done. And then in the link layer, we have the data link control, which is framing, data transparency, and error control is happening here in this layer. And then for physical layer is we have the mechanical and electrical network interface connections. So these are mostly the hardware. And then between the physical layer and the data communication network, these are the physical connection to network termination equipment, such as, for example, cables. We have wireless access points and routers. So we have the OSI network message. So, but physically, a message starts at or, so this is the message, above the application layer and is passed through each lower level in turn. Each layer may modify the message and include message header data for the equivalent layer on the receiving side. Ultimately, the message reaches the data network layer and is transferred as one or more packets. The data link layer of the target system receives this data, and the message is moved up through the protocol stack. And then it is analyzed, modified, and stripped of headers as it progresses. It finally reaches the application layer for use by the receiving process. So again, the OSI model, this formalizes some of the earlier work done in network protocols, but was developed in the late 1970s and is currently not in widespread use. So the most widely adopted protocol stack is the TCP/IP model, or the Transfer Control Protocol or Internet Protocol, which has been adopted by virtually all Internet sites. You will see the reason why as to TCP/IP model is adopted compared to OSI model. So the TCP/IP protocol stack has fewer layers. So that is the first advantage of TCP/IP. Fewer layers than the OSI model. Theoretically, because it combines several functions in each layer, it is more difficult to implement but more efficient than OSI networking. And then the relationship between the OSI and TCP/IP models is shown in the next slide, as we can see. So, for TCP/IP, it only is composed of 3 layers. Okay, then for OSI, we have 1, 2, 3, 4, 5, 6, 7. So the equivalent, so physical and data link is not defined in TCP/IP as session and presentation layers. But for TCP/IP protocol, IP is equivalent to network. Then TCP/UDP is for the transport. So UDP is user datagram protocol. And then we have the application. It can be HTTP or Hypertext Transfer Protocol. DNS, of course, is the main name system, the telnet. And then we have the SMTP, the Small Mail Transfer Protocol. And then the FTP, or the File Transfer Protocol. Okay, TCP/IP example. So every host has a name and an associated IP address, which is the host ID. It is hierarchical and segmented. So sending system checks routing tables and locates a router to send packet. Routers use a segmented network part of host ID to determine where to transfer the packet. This may repeat among multiple routers. And then destination system receives the packet. Packet may be complete message, or it may need to be reassembled into larger message spanning multiple packets. Okay, next is we have within a network, there's a question, how does a packet move from sender, host, or router to receiver? So every Ethernet or Wi-Fi device has a medium access control or MAC address. So what is this MAC address? So this is also unique to every devices that can connect to a network, just like the IP address. So what's the use of this medium access? Actually, I tried to use this in one of our routers in the internet connection. The name is MAC filtering. So MAC filtering is you're going to register the MAC addresses of all the computers that connect to the network. If you include them in the list, meaning that they are the only computers that can connect to the internet. I actually experimented on this. Then when my brother went here and then connected to the internet, actually he can connect because he knows the password, our wireless connection password. Then he asked, why is it our internet connection? It is detected that it has an internet connection, but why? He asked me like that. Why can't I connect? So, so that's the use of the MAC filtering. So you can let others to connect to your internet to the wireless connection, but because of they are not included in the list, or it's not, they are not an exception. So even though it can be connected, the device can be connected to the wireless connection, but the device will not be given an internet connection. So it's another tip for you. For example, you have an internet connection at home and you want to control who can access your internet connection, because of course there are hackers. You can use that feature of course you have to modify and you have to know the user, the admin and password for the router or for the ISP's control for your for that particular in your router given by your ISP. So let's continue. So two devices on same LAN communicate via MAC address. if a system needs to send data to another system, it needs to discover the IP to MAC address mapping. So this uses the Address Resolution Protocol, or the ARP. So by the word itself, Address Resolution Protocol is we have to map the IP to MAC address. And then a broadcast uses a special network address to signal that all hosts should receive and process the packet, so not forwarded by routers to different networks. So that's the problem with that. So, so aside from the example that I've given you, the application of medium access control, so it is a unique byte number assigned to every Ethernet device, allowing it to be located by packets sent across a LAN network. So this is the composition of an Ethernet packet. So this is the number of bytes needed for preamble or start of packet is we have 7 bytes. So each byte pattern of 101010, and then byte it needs 1 byte. So start of the frame delimiter. So the pattern 10101011, and then 2 to 6 bytes are needed for destination address. This is the Ethernet address or broadcast. Then 2 to 6 bytes are needed for source address or the Ethernet address. Then 2 bytes for length of data section or length in bytes. So the data can have can be 0 byte, or the largest is 1500 bytes of data, which is the message data. And then 0 to 46 bytes are needed by the pad, which is optional. Message must be greater than 63 bytes long. But example, the message is already big enough. So this is the padding can be can it's there's a you cannot apply, or rather uh, that's why it's optional. If the message is already that big, you don't need to apply the padding. And then 4 bytes for frame checksum for error detection. So next is we have the transport protocols UDP and TCP. So once a host with a specific IP address receives a packet, it must somehow pass it to the correct waiting process. Transport protocols TCP and UDP, or the user datagram protocol, identify receiving and sending processes through the use of a port number, allows hosts with single IP address to have multiple server or client processes sending or receiving packets. So the following are well-known port numbers that are used for many services. So for file transfer protocol is we have port 21. Then for SSH actually is called Secure Shell Protocol. It is a cryptographic network protocol for operating network services securely over an unsecured network. So it's port 22. So SMTP, the small mail transfer protocol, is port 25. So it's responsible for our email messages. And we have the HTTP, or the hypertext transfer protocol, which is port 80. So transport protocol can be simple or can add reliability to network packet stream. Okay, I've already mentioned user datagram protocol, or UDP. So it is said here that UDP is unreliable, bare bones extension to IP with addition of port number. So why unreliable? So because it's connectionless. So since there are no guarantees of delivery in the lower network or the IP layer, packets may be lost. So that's why UDP is unreliable. Packets may also be received out of order. And then another is UDP is also connectionless. No connection set up at the beginning of the transmission to set up state. And also, no connection tear down at the end of transmission. So UDP packets are also called datagrams. So this is an example of a illustration of a UDP drop packet example. So we have this for the client initial request for data, and it used UDP. So it will connect to the server for request. Server starts sending data to the client. So it sends data and then drop the packet. So for dropping that packet, it may be lost and it will not be sent again for UDP. So that's the problem. And another problem, as in mentioned in the previous slide, the packets may arrive out of order and it will not be arranged before it will be read or used by the client or the user. So what about transmission control protocol? So TCP compared with UDP is both reliable and connection oriented. In addition to port number, TCP provides abstraction to allow in order uninterrupted byte stream across an unreliable network. Whenever host sends packet, the receiver must send an acknowledgement packet. So acknowledgement to notify the sender that the receiver received the packet. If acknowledgement not received before a timer expires, the sender will resend. So that is the step for if the sender does not receive any acknowledgement, so it will think that it means that the receiver did not receive the packet, so the sender will resend it again. And then there is a time interval. And then sequence numbers in TCP header allows receiver to put packets in order and notice missing packets. Then connections are initiated with series of control packets called a three-way handshake. So what is a three-way handshake? Actually, three-way handshake happens like this. For example, you have a client and server. The client will initiate connection by means of synchronization of sequence number or SYN, and then the server will react with that synchronized sequence number. So its reaction is synchronized also plus acknowledgement to the client. And then the client will acknowledge the SYN plus acknowledgement from the server, and the connection is already established. So for you to further understand the three-way handshake, example, in my computer, I want to download a file from the site. Of course, that website has a server. So if I click, for example, the download button, so what happens is that my computer will send a request to the server or the SYN or the synchronized sequence number requesting for that file. And then the server will synchronize also plus acknowledge that request. Okay? And then it will send back to my computer, for example, and then my computer again will send an acknowledgement that the synchronized sequence number and acknowledgement is received. Then after that, the server will already send that the will permit the client to download the data. So that is the three-way handshake. So for us, we never realized that for us, downloading the files, it happens just like just click the button and then you're going to download the file. You don't know what is happening under. So all um, all internet transactions always have this three-way handshake at first. So for example, you click the download button, for example, and then it commences downloading. It means that the three-way handshake is fast for the client and the server. So the same with, for example, you're accessing a website. They're also using three-way handshake. It's not just applicable with downloading files. So if you have an error that shows, example, if you encountered the server refused to connect. So what happens is that your computer, you're trying to access the site or you're trying to access a resource from the server. So that's the synchronized sequence number. But the server did not acknowledge back the synchronized plus acknowledgement to your computer. So it means you from the three-way handshake, you only done the step one or the stage one of the three-way handshake. So that's why the server refused to connect. It does not it really just means that the resource that you're trying to download is restricted for members or if you're going to log in. So that's the implications of that. So connections also closed with series of control packets. So we have the TCP data transfer scenario. So again, we have the client and server. So the client has a request for data. So we have the data sequence 904. So the server starts sending data to client. So again, there's an acknowledgement for the uh, coming from the server, and it also sends the synchronized sequence number. The data sequence is equal to 126, and then the client will acknowledge the sequence is equals to 126 to notify the server that the client has received that data sequence. Then after that, it will already send data. So we have here, so this while sending the data, it was dropped off. So the data sequence 127. So the server will automatically wait for the client to have an acknowledgement. But since um, the server did not receive any acknowledgement from the client, so it will resend data again, the sequence 127. So this is the time in which the server will wait for the acknowledgement to be sent back. But of course, if if it does not happen, then the server will resend again the data with this sequence number. And then, good for that, the client has received the sequence number, so acknowledgement for 127. And then again, the data is sent, the sequence 128 is sent to the client. But since the client receives it and acknowledgement is passed, but then what happens, it was dropped off somewhere in the network. So what happens again, since the server did not receive the acknowledgement, even though it is already sent by the client, it will resend again the data with sequence 128. So for TCP, the server will not know if it is the server's fault, or is it dropped while sending it to the client, or the acknowledgement has lost in the connection. So the server has no other way. The For them, what is important, if it did not receive any acknowledgement from the client, then it will resend it back. And then, of course, since it is already sent again, then the client sent again an acknowledgement for 128, and it's received by the server. So imagine, this is only from one client to server. Server has many clients, and imagine this transaction. This is only for one client. Imagine for if there are um, end users who are accessing the server simultaneously. It's very complicated actually. So let's continue with this. So for the TCP, receiver can send an cumulative acknowledgement to acknowledge series of packets. Then server can also send multiple packets before waiting for acknowledgement. So this is also possible, and takes advantage of the network throughput. So the flow of packets regulated through flow control and congestion control. So flow control is prevent sender from overrunning capacity of the server. So it has some prior information that this client can only um, can only occupy or accommodate that data. And while the congestion control approximates congestion of the network to slow down or speed up packet sending rate. So it depends upon, for example, you can see in our real world situation, if it's there's a traffic jam, of course. So to avoid congestion, so you have to slow down for this sending the data. But if it's very there's no traffic jam, and then you can send it faster. So okay, next is we have the network oriented operating systems. We have two main types. We have the network operating systems. These are users are aware of multiplicity of machines. So for a network operating systems, they do not consider the machines using the NOS as one entity, or one cluster. While the distributed operating systems, users are not aware of multiplicity of machines. As long as for the users are using the services efficiently, he or she does not care if the services has really many servers. So first is we have the network operating systems. Users are aware of multiplicity of machines as it is mentioned in the previous slide. So access to resources of various machines is done explicitly by remote logging into the appropriate remote machine by using the SSH or the Secure Shell Protocol. So we have an example here, the command, and then transferring data from remote machines to local machines via the file transfer protocol mechanism or the FTP. So what's the difference of downloading a file in a website and the FTP? For FTP, before you can download or transfer the file, you need a username or password or authentication for you to have an access for that file. That's the FTP. Then upload, download, access or share files through cloud storage. Then users must change paradigms, establish a session, give network-based commands, and use a web browser. So it is more difficult for users because I think most they are familiar with using just a web browser. So while distributed operating systems, so again, users are not aware of multiplicity of machines, access to remote resources similar to access to local resources. So we have the data migration. So the transfer of data by transferring the entire file or transferring only those portions of the file necessary for the immediate task. And then we also have another term which is the computation migration, transfer the computation rather than the data across the system. So computation migration is done via remote procedure calls or the RPCs or via the message system. So we also have process migration. So execute an entire process or parts of it at different sites. So why this process migration is done? It's because of load balancing. So distribute processes across network to even the workload. Another is computation speed up. Sub-processes can run concurrently on different sites. And then hardware preference. Process execution may require specialized processor. So that's why you need to migrate the process to the server or to the computer which has this specialized processor or hardware. And then we also have software preference. Required software may be available only at a particular site, just like with the hardware preference. And data access, run process remotely rather than transfer all the data locally. So you can consider the World Wide Web as a distributed system that uses this mechanism. Okay, so design issues of distributed systems. So we investigate three design questions. We have the robustness, transparency, and scalability. For robustness, can the distributed system withstand failures? Then for transparency, can the distributed system be transparent to the user both in terms of where files are stored and user mobility? And then another is we have the scalability. Can the distributed system be scalable to allow addition of more computation power, storage, or users? So we're going to discuss this one by one on the next slides. So first for robustness, so hardware failures can include failure of a link, failure of a site, and loss of a message. So a fault-tolerant system can tolerate a certain level of failure. Degree of fault tolerance depends on design of system and the specific fault. The more fault tolerance, of course, the better. So it involves failure detection, reconfiguration, and recovery. So the example that I have mentioned is the Yahoo Philippines. So once one of the server of Yahoo Philippines is detected, so users who are accessing Yahoo Philippines server will be directed to other servers. So that's reconfiguration. And while it was reconfigured and it was redirected to other servers, of course, uh, recovery will be done for that server that has a problem. So that is recovery. Okay, next is we have failure detection. So detecting hardware failure is difficult. So to detect a link failure, a heartbeat protocol can be used. So how does this heartbeat protocol done? So we have this one. Assume site A and site B have established a link. At fixed intervals, for example, every 5 seconds, it's just an example, each site will exchange an I am up message indicating that they are up and running. So they always exchange at fixed intervals. I am up, I'm okay. For example, if there are two people. Next is, if site A does not receive a message within the fixed interval, it assumes either letter A, the other site is not up, site B, or the message was lost. Or site B is okay, but there is a problem with their connection, direct connection. So since site A did not receive any message from site B, so site A can now send an RU app message to site B. So, if site A has already sent the RU app message, if site A does not receive a reply, it can repeat the message again or try an alternate route to site B if it is available. So, again, site A and site B have a direct connection. Site A send an RU app message, but still the site B is not yet replying. So, site A may connect to an alternate route to site B. So, next, if site A does not ultimately receive a reply from site B, it concludes some type of failure has occurred. So, again, let's go back to what if the site A messages site B through an alternate route or route, and then site B replied. So, it means site B is up and alive, and it can be determined that the problem is not with the site but with the direct connection between site A and site B. So let's go back here. So these are the type of failures. For example, site A does not ultimately receive a reply from site B. So site B is down. Site B is down if, the conclusion, if you already use the alternate route to site B, then still no reply. So definitely site B is down. Next, the direct link between A and B is down. Also because with the example, you use the alternate route to site B and site B has replied. So meaning the direct link between A and B is down, not actually site B. And another is the alternate link from A to B is down. So this is another what if the alternate route is also down, a worst case situation. So if A does not receive any message from B, it's either the alternate link is also down and site B is down. And worst, another unfortunate that will happen is the message has been lost. So however, site A cannot determine exactly why the failure has occurred. It only can detect the failure, but it will never know why does this failure occurred. Okay, next is we have reconfiguration and recovery. When site A determines a failure has occurred, it must reconfigure the system. So if the link from A to B has failed, this must be broadcast to every site in the system. So if the link, the other site must know it, that there is a problem link between A to B. If a site has failed, every other site must also be notified, indicating that the services offered by the failed site are no longer available. So that's why if the site has crashed or has a problem, there will be a redirecting of access whenever that site will be accessed by a user or client. When the link or the site becomes available again, this information must again be broadcast to all other sites to notify that the problem has already been solved. So next is we have transparency. The distributed system should appear as a conventional centralized system to the user. So the user must not know that it is composed of many machines. So user interface should not distinguish between local and remote resources. So an example of that is the network file system or NFS. And then user mobility allows user to log into any machine in the environment and see his or her environment. Example is the Ldap. So as you can remember, Ldap is lightweight directory access protocol plus desktop virtualization. So next is we have scalability. As demands increase, the system should easily accept the addition of new resources to accommodate the increased demand. So reacts gracefully to the increased load. And then adding more resources may generate additional indirect load on other resources if not careful. So data compression is for the data to occupy lesser space, or deduplication, removing duplicates, can cut down on storage network and network resources use. So scalability means that if your distributed system can can expand, can add more sites or servers or machines, and there will be no problem for the workload. So it means your distributed system is scalable. Okay, if we have distributed operating systems or distributed system, we also have distributed file system. So it is also called the DFS. It is a file system whose client, server, and storage devices are dispersed among the machines of a distributed system. Should appear to its clients as a conventional centralized file system. And then key distinguishing feature is management of dispersed storage devices. So for DFS, we have service, a software entity running on one or more machines and providing a particular type of function to a priori unknown clients. And then we have a server, service software running on a single machine. Then we have a client, process that can invoke a service using a set of operations that forms its client interface. And then a client interface for a file service is formed by a set of primitive file operations such as create, delete, write, and read. And then client interface of a DFS should be transparent, which is not distinguished between local and remote files. So the client interface, for example, a user, the user does not need to know if this file is located to the server in Japan and the other is located in the server in Korea, as long as the client can access that files efficiently. And then sometimes lower level inter-machine interface need for cross-machine interaction. And then two widely used architectural models include the client-server model and the cluster-based model. So as we already seen, the client-server is we have a server that has the resources and the client will access on that. So that's the client server. Again, the real world analogy for that is a mother and a baby or a child. And then we have the cluster-based model, which is a resource sharing model where all systems are equal users and providers of resources. So what are the challenges that are included? We have the naming and transparency, the remote file access, and caching and cache consistency. So we're going to discuss it later on, the challenges. So next is we have the client server DFS model. So servers store both files and metadata on attached storage. Clients contact the server to request files. Then the server is responsible for authentication, checking file permissions, and delivering the file. Changes client makes to file must be propagated back to the server. So any changes should be made, or again that it is said that propagated back to the server to avoid file inconsistency. Popular examples include the NFS or the network file system and the Open AFS or the Open Andrew file system. So design suffers from single point of failure if server crashes, because the server is the sole um, the sole controller for the resources. And then if this crashes, then the resources will not be accessed by the clients. Then server presents a bottleneck for all requests of data and metadata, specifically if you only have only one server, meaning bottleneck. For example, you have one server and your clients are 1,000. So there will be actually a bottleneck for the server because the server must accommodate this 1,000 servers. So could pose problems with scalability and bandwidth. So this is the client server DFS model. So assuming that you only have one server, then the clients are accessing through a network. They are not actually located at the same site. Okay, next is we have the cluster-based DFS model. So built to be more fault-tolerant and scalable than client-server DFS. So examples include the Google file system, the Hadoop distributed file system. So clients connected to master metadata server and several data servers that hold chunks or portions of files. Metadata server keeps mapping of which data servers hold chunks of which files, as well as hierarchical mapping of directories and files. And then file chunks replicated n times. So cluster-based model, this is more efficient because this can handle big data. So this is an illustration of how the cluster-based model is set up. So we have the client and then the data servers and metadata all connected to a network. And then as it is described in the previous slide, the meta server has the list. Of course, this file, for example, this file is divided into three chunks, which is this first chunk to this data server, the second chunk is here, and then the third chunk is on this data server. So the meta server data must have a list in which this file chunk is in what where is the location of that data server, the one holding this chunk. So that is the cluster-based DFS model. So GFS design or the Google file system was influenced by following observations. Hardware component failures are the norm rather than the exception, of course, because hardware from over time, it is a hardware, then it will have a defect later on. So and should be routinely expected. Files stored on such a system are very large, and then most files are changed by appending new data to the end rather than overwriting existing data. Redesigning the applications and file system API increases system flexibility. It requires applications to be programmed especially with a new API. Then modularized software layer MapReduce. It can sit on top of GFS to carry out large-scale parallel computations while utilizing the benefits of GFS. So the Hadoop framework are also stackable and modularized. So that's why Hadoop actually is very popular for big data. So that's why cluster-based is very convenient and advantageous if you store big data. Okay, next is the challenges. As I've said, we have first the naming and transparency. So for naming, mapping between logical and physical objects. And then we have multi-level mapping, abstraction of a file that hides the details of how and where on the disk the file is actually stored. And then a transparent DFS hides the location where in the network the file is stored. So actually, for us users, we don't care where does this file is stored as long as we can use and download that file, right? And then next is for a file being replicated in several sites, the mapping returns a set of the locations of this file's replicas. Both the existence of multiple copies and their locations are also hidden. So for naming structures, we have location transparency. File name does not reveal the file's physical storage location. And then we also have the location independence. File name does not need to be changed when the file's physical storage location changes. In practice, most DFS use static, location transparent mapping for user level names. So some support file migration such as the OpenAFS. Hadoop supports file migration but without the following POSIX standards, hides information from clients, and Amazon S3 provides blocks of storage on demand via APIs, placing storage dynamically and moving data as necessary. Then for the naming schemes, we have three approaches. The first approach is files named by combination of their host name and local name. It guarantees a unique system-wide name. This naming scheme is neither location transparent nor location independent. The second approach is attach remote directories to local directories, giving the appearance of a coherent directory tree. Only previously mounted remote directories can be accessed transparently. And then another is single global name structures spans all files in the system. If a server is unavailable, some arbitrary set of directories on different machine also becomes unavailable. So next is we have remote file access. So consider a user who requests access to a remote file. The server storing the file has been located by the naming scheme, and now the actual data transfer must take place. So we have this remote service mechanism is one transfer approach. So what does this do? So a request for accesses are delivered to the server machine performs the accesses, and their results are forwarded back to the user. So one of the most common ways of implementing the remote service, this remote file access, is by using the RPC or remote procedure call paradigm. So next is reduced network traffic by retaining recently accessed disk blocks in a cache so that repeated accesses to the same information can be handled locally. So if needed data not already cached, a copy of data is brought from the server to the user, and then accesses are performed on the cached copy, then files identified with one master copy residing at the server machine, but copies of or parts of the file are scattered in different caches. So it's like the caching in which, for example, if this is recently used, it will stay on the cache. It's also the same with remote file access. But of course, remote file access is happening in a distributed operating system or file system in which there are two or more machines that are working. So the cache consistency problem, keeping the cache copies consistent with the master file. So that's why if you're going to change the copy of this file, it should be reflected back to the master file. It could also be called network virtual memory. So network virtual memory is actually used for DFS caching. So distributed computing features similar to virtual memory but with the backing store on a remote system. So cache location, so disk versus main memory. So the advantages of disk caches, so it is more reliable. Cached data kept on disk are still there during recovery and don't need to be fetched again. So that is the advantages of using disk cache in remote file access. So what is the advantage, on the other hand, of the main memory caches? Permit workstations to be diskless. Data can be accessed more quickly. Performance speed up in bigger memories. And then server caches used to speed up disk I/O are in main memory regardless of where the user caches are located. Using main memory caches on the user machine permits a single caching mechanism for servers and users. So next is we have the cache update policy. We have the write data through to disk as soon as they are placed on any cache. It is reliable but poor performance because for every update, you have to write through to the disk. And then we have another one is the delayed write or write back. Modifications are written to the cache and then written through to the server later. So write accesses complete quickly. Some data may be overwritten before they are written back, and so need never be written at all. And then it is poor reliability compared to write through that it is reliable. Delayed write is unreliable actually. Unwritten data will be lost whenever a user machine crashes. So the variation is scan cache at regular intervals and flush blocks that have been modified since the last scan. And then another variation of delayed write is write on close, writes data back to the server when the file is closed. So it is best for files that are open for long periods and frequently modified. So next is for consistency. Is locally cached copy of the data consistent with the master copy? So to answer that, we have client-initiated approach. So client initiates a validity check, and then the server checks whether the local data are consistent with the master copy. Or the other hand is we have the server-initiated approach. Server records for each client or the parts of files it caches. When server detects a potential inconsistency, it must react. So in a cluster-based DFS, cache consistency issue are more complicated due to the presence of metadata server and replicated file data chunks. So for the Hadoop DFS, allows append-only write operations. There are no random writes and a single file writer. For Google FS, allows random writes but with concurrent writers. So complicates write consistency guarantees for GFS while simplifying it for HDFS. So of course, cache consistency is very complicated with cluster based because the metadata server has the list of the chunks where does these chunks are located, which data server holds that chunk. So of course it will be more complicated compared with the other setup. So we're already finished with chapter 19. So do you have any questions for this lesson? So if you do have, please feel free to comment below. And I hope you learned something all about the technicalities of the network and distributed systems, such as the distributed operating systems and the distributed file systems. So how they work and what are the actual applications of distributed file systems. So please don't forget to subscribe to my YouTube channel. So thank you very much. Good day and stay safe.